Hi folks, welcome back. I hope you're all doing well. So today I thought I'd take a break from the long streak of videos on LLMs and get back to an old favorite topic of mine, which is programming languages. I saw this really interesting paper on a variant of Python called static Python, and it tries to improve the performance of Python by adding static types to it. The really interesting thing about this paper is that you'll see some of the authors are from Brown and others are from Meta. They've actually implemented this and used it in an industrial context. They've used it for the serving backend for Instagram and achieved some very promising results out of that. We've all seen the rise of gradual typing in many programming languages over the last 5 or 6 years. The most prominent example, of course, was TypeScript. It was a strict superset of JavaScript, but it added types. Another more recent example that came after TypeScript was the addition of optional type annotations to Python. And then we had these static type checkers like MyPy or Pyre and so on that would statically check if those type annotations were being respected by the items that they were annotating. And this whole methodology was called gradual typing because you didn't have to put type annotations on your entire code base. You could just sprinkle type annotations in the places where you thought it was manageable to do so and get some benefit by the static analysis giving you places where the types were not respected, and then you could go fix your code. In the case of Python, at least, all this type checking did not translate to any difference at runtime. This was a purely static analysis. Now, the problem with gradual typing, of course, is that it's purely optional and hence it is unsound. Unsound in the sense that incorrectly typed programs will make it through the type checker and will blow up at runtime. But then if you think about it, it's hard to get away from that if you're saying that you only want to type annotate a subset of your code base, hence the name gradual typing. The authors of this paper have taken a big step forward by developing a sound type system, but for a subset of Python. And then they couple this with a runtime system and a just-in-time compiler that uses this type information to drive optimizations. What do I mean by that? In pure dynamic Python, if I assign an integer value, say 1, to a variable x, and then perform some arithmetic operations on x, all of those operations will use a boxed type. So you're not doing native integer operations on it because at runtime, you're not sure if x indeed does always hold an integer. But now if you have a sound type system where the annotations tell you for sure what type a particular variable holds, those operations don't need to operate on a boxed object anymore. You could, if it was an integer, use the native integer operations, and that would, of course, make it much faster. There is a price to be paid for this, however, and that is that these kinds of what the authors call concrete types that ensure gradual soundness require some of the rest of your code base to change. Let's look at a concrete example to make things clearer. On the left here, you have a small snippet of Python code that has a function that takes in a dictionary and returns the element of that dictionary corresponding to the key A, where A is a string. So it looks like this function takes in a dictionary where the keys are strings and the values are integers. Now the snippet in the middle, you'll see that we've used the typing module and imported the dict type from that module and then annotated our input parameter x with a dictionary type going from strings to ints. This is what you would typically do today and then run a static type checker like MyPy on. In static Python, however, this is also enforced at runtime, and static Python would enforce this type at runtime, but this type dict is called a shallow type because you're still using a lot of runtime checking, and the dictionary data structure being used is Python's regular dynamic untyped dictionary data structure. And now let's look at this rightmost piece of code where we're importing a new dictionary data type. So this is checked dictionary, which is a new concrete data structure that's provided by static Python, and it ensures that its keys and values are of these given types. So this is not Python's built-in dictionary type. It is guaranteed to contain keys and values of the correct types, and that enables a whole lot of optimizations when you're doing lookups on this dictionary. The price you pay for that is that you have to change the code around F that calls F. So previously you could just call F with any Python dictionary, whereas now you have to specifically instantiate a new dictionary of the checked dictionary type. Static Python currently supports the basic scalar types like integers, Boolean strings, and a few data structure types like lists and dictionaries and so on, and classes. So they're not going for the full coverage of all types, but just the most commonly used ones that they're hoping to get a lot of performance optimization out of. Again, note that static Python is intentionally making a trade-off to break some backward compatibility in order to propagate strong typing information, especially at the boundary between typed and untyped code. It inserts casts. Now note that what we have in static Python is a combination of the unsound gradual typing that we were used to and also increased soundness guarantees. The authors call this a multi-level type system. The old style types that the authors called shallow types are backward compatible with existing Python code, but then can't be used for actually optimizing the performance of that code. Now, if you go beyond these shallow types, like say the built-in dictionary data structure, and start using these new concrete types like the new checked dictionary we just saw, it gives you much stronger type guarantees and also lets the optimizer make that code much faster. But the price to be paid is that you have to make changes beyond that code as well. And this overall system where programmers can crank the dial between untyped code and then gradually increasing the soundness level of their code with concrete types is what the authors call gradual soundness. And this entire type system is paired with a new runtime. They call it Cinder, and it's based on the CPython 3.8 runtime, but it adds several bytecodes to Python's built-in set of bytecodes and a JIT compiler and several mechanisms to deal with all this type information. I'd encourage you to read the paper for all the full details. Alright, so was all of this worth it? What was the payback? They've used this on the Instagram web server to serve requests in production. And at Instagram scale, they got about a 3.7 improvement in CPU efficiency. Now, I Googled this and it looks like Instagram has more than 2 billion monthly active users, and that requires a significant data center footprint. At that scale, a 3.7% improvement is absolutely massive. It looks like the Instagram team gradually adopted static Python by adding these new concrete types to their most performance sensitive modules and gradually building up from there. So that was a quick look at static Python, a Python variant that uses concrete types that enable performance optimizations, and they actually use this in a very large industrial setting, so it looks pretty promising. I hope you enjoyed that, and if you like content like this, please like the video, please consider subscribing to the channel. I'd love to hear your comments, and I will see you all next time. Thank you very much.